In this lesson, we will look at gravitational fields, which forms part of the physics syllabus. So forces are long-range forces. There's no contact that is required for the force to be exerted in a gravitational field. So when we look at universal gravitation, we look at Newton's law of universal gravitation. So gravitational force is always attractive. When you have two objects, there will always be a force that attracts them towards each other. The force of attraction is directly proportional to the product of the masses that we simply get from our equation of F equals G m1 m2 over r squared. So our force is directly proportional to the product of our masses, and the force is inversely proportional to the square of the distance between their centers. Again, we simply get that from the formula where F equals G m1 m2 over r squared. Therefore, F, being our force, is inversely proportional to r squared. When we look at the field lines around two masses, where we have mass 1 over here and mass 2 over here, we have field lines towards the center of the mass. Now, when we draw the field lines always go from our smaller mass to our larger mass, as the smaller mass is attracted to the larger mass. Now, field lines are directly proportional to your mass, so you will have a greater number of field lines around your larger mass and a smaller number of field lines around your smaller mass. And we must remember that they're always towards the center of the mass and perpendicular to the surface of the mass. So we have our formula. The gravitational force measured in newtons is equal to G, which we know is a constant at 6.67 times 10 to the negative 11, times our mass 1 and mass 2, which is measured in kgs, over r squared. R is our distance between the centers, and we must always put that in meters. And we must know that G, which is our constant, is measured in Newton meters squared, kilograms to the minus 2. Now, just a point with the formula, you must always remember to put your values in the right format and in the right units. So your mass must always be in kilograms and your distance must always be in meters. Often they'll give you a mass in grams or a distance in kilometers, and you must always convert before you put it into the formula. When you're dealing with these numbers, there's often large exponents, so it's easiest to use your exponent button on your calculator. So you simply press your times 10 to the x and you put your exponent in as a value, as a number, not as an exponent. We look at Newton's law of universal gravitation. So as we've said, every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now that definition is simply the worded definition for the formula that we are given for Newton's universal law of gravitation. When we look at gravitational force and weight, so weight is the gravitational force that Earth exerts on an object on or near its surface. When we look at weight, we label it as Fg, which is simply symbolic of weight, and weight is our mass in kilograms of an object times g, which is the acceleration due to gravity, which is a constant on the formula sheet, and it is 9.8. When we look at the attraction of Earth, we look at Fg equals g, the constant g, m, with m being the Earth's mass over r squared, and we look at weight being mg, and we can get, from these two equations, we can get that if Fg equals mg and Fg equals g, big M over r squared, we can equate them and we get g to be g times m being the mass of the Earth or the mass of any planet you're trying to find the acceleration due to gravity on, over r squared. So g is simply your gravitational field strength, your gravitational acceleration as we've said, which is 9.8 on Earth, but they will sometimes ask you to calculate it on other planets, and this is how you will do that. So your greater value of g simply means there's more force acting per unit mass on that planet. And you must know that g is not directly proportional to the mass of the object. It's independent. It is always 9.8 on Earth, and it will be constant on any planet. We look at gravitational fields. So your acceleration due to gravity is g, as we've said. is known as the gravitational field strength. Your gravitational field strength is defined as the force acting per unit mass on an object placed in a gravitational field. When you are asked to draw a gravitational field, your field lines must be perpendicular to the surface of your object, as we can see here. If you have two objects, your field lines must always go from your smaller to your larger object. Your field lines never cross, they are always perpendicular. They point towards the center of the mass, as we can see, and they are closer together towards the mass, and further away they are more spread out and further apart. So now we just need to look at the difference between mass and weight, because a lot of people get confused by this. So mass is scalar. There is no direction. It is not a force. It is constant throughout the universe. If you have a mass of 55 kilograms on Earth, you will have a mass of 55 kilograms on Mars. However, if we look at a weight is a vector quantity that includes a direction. It is a force. So this varies depending on your position. You may have a weight of 45 newtons on Earth and a weight of 30 newtons on Mars. And as we can see, that is dependent on your position. You will also have a different weight on Earth's surface than you will at 5,000 meters above the Earth. So that is just important to note, and sometimes they will try and trick you into realizing that mass and weight are two different concepts.